Okay, we're going to look at a specific type of hyperbola, the one that we're used to seeing, y equals 1 on x, which is what's called the rectangular hyperbola. Basically, it's defined this way. Any hyperbola whose asymptotes are perpendicular to each other is what we call a rectangular hyperbola. Now, if we put it in terms of the hyperbolas we've been looking at, we've said the asymptotes were plus or minus b on ax. Okay? So what we're saying is those slopes would multiply together to give negative 1 because they're perpendicular to each other. Well, if that's true, b equals a. So basically we're talking about a hyperbola where the coefficients are the same magnitude but opposite in sign. So the hyperbola will end up with the equation x squared minus y squared equals, well, a squared, some number. So the eccentricity, well, e squared will then be, instead of a squared plus b squared, it'll be a squared plus a squared on a squared. So it turns out to be the square root of 2. So every rectangular hyperbola has eccentricity of square root of 2. And it has been known for them to give you a rectangular hyperbola and say, find the eccentricity, just to see who wastes time and goes through and derive it, and who just writes down square root of 2. Now, so here is our x squared minus y squared equals a squared. We're going to turn it into what we're used to seeing, just to prove that, yes, indeed, they are, in fact, the same graph. What I need to do is to rotate this graph 45 degrees. Okay? Remember, we now know the asymptotes are y equals x and y equals minus x, because we said a was equal to b. So b on a becomes a on a, which is 1. And y equals x has a slope of 1. We want to turn that into the y-axis. Y equals negative x, we want to turn to the x-axis. So we're going to rotate anti-clockwise. So we're going to go back to complex numbers. If I now think of this as the Argand diagram, if we wanted to rotate things, it was like multiplying with our vectors. So if I multiply our random point by cis 45, if you rotate, you multiply by cis of the rotation. The most common one we saw was multiplication by I, which was cis 90. Okay, so x plus iy, I'm going to multiply by cos 45 plus I sine 45, which of course is 1 on root 2 plus 1 on root 2i. Expand that whole thing out, and I get x minus y on root 2 and x plus y on root 2. Remember, I want to turn it into the x-axis and the y-axis, so I've got to transform this. So if I let capital X equal x minus y on root 2, and I let capital Y be x plus y. So what I'm saying is the new x coordinate when I rotate it must be x minus y on root 2, because it was the real part. The new y coordinate will be x plus y on root 2. It'll be the imaginary part. And sure enough, when I multiply x times y, or the new x times y, I get x squared minus y squared on 2. But we said the equation, little x squared minus little y squared, was equal to a squared. So in fact we get our new one, once we've rotated it, the new x times the new y does in fact equal some constant number. So xy equals a constant, which is what we recognise as our normal hyperbola. Now don't panic, they're not going to ask you to actually turn it into there, but that's just showing that, yeah, it is in fact the same hyperbola that we've been working with. But where are all the focus and all these sort of points going to turn into? Well, the focus originally was plus or minus AE naught. When we rotate it, AE is root 2. So when I rotate it, multiply it by 1 on root 2 plus 1 on root 2i, I get a plus ai, so the focus is AA. Makes sense. You'd think the focus would end up on the line y equals x, because that would be the axis of symmetry of the rectangular hyperbola. The directrix, what happens? A little bit more work here to work this one out. We know originally it was plus or minus a on e, which now we know to be a on the square root of 2. Okay. The directrices are parallel to the y-axis at the moment. So when we rotate them, they will end up being parallel to y equals negative x, because we're rotating 45 degrees. So I know that it'll be in the form x plus y plus some constant number will equal 0. Okay. I also know, before I moved it, the distance between the two directrices will be 2a over the square root of 2, because each one has the equation a on root 2 and minus a on root 2. Add them together, we'd have 2a on root 2. Now when I rotate them, that distance isn't going to change. So the distance from the origin to the directrix must be a on root 2. Now it doesn't matter that I've rotated it, it's still going to be a root 2. In other words, the perpendicular distance from the origin to the directrix. Okay, that now allows me to find k. Because if I say the perpendicular distance to this line, x plus yk, from the origin, I know the answer is a on root 2, then the root 2's cancel, and something very nice happens. We simply get that the absolute value of k is equal to a, x is plus or minus a. So the directrices will be x plus y is equal to plus or minus a for our rectangular hyperbola. So all right, let's just summarise all that. So the rectangular hyperbola, once we've transformed it back to what we were used to seeing with the x and the y axes as asymptotes, it'll be xy equals a half a squared, where the focus, or foci, plus or minus a, the directrices x plus y is plus or minus a, and the eccentricity will always be the square root of 2. Now, the parametric coordinates, this one we do like the parabola, in terms of not the auxiliary angle, but just a letter t. And it's more convenient. Instead of thinking of it as a half a squared, we just think of this as some constant squared, because then the parameters are very simple. One is going to be c times t. The other one will be c divided by t, because when you multiply x times y, you get c squared. Okay? So the parametrics, x equals ct, y equals ct, but that's when we write it as xy equals constant squared, so c squared, not xy equals half a squared. We use a half a squared when we want to work out the foci or the directrices. When we're playing with the parameters, we use c squared. The tangent, when you work it out, turns out to be x plus t squared y is 2ct. And the normal, look at that lovely expression, t cubed x minus ty is c to the outside of t to the power of 4 minus 1. Okay, very old question, but it's good because it's palindromic, 1991. Makes sense because there's all this symmetry happening. First thing they simply wanted us to do was draw this sketch. What a very nice gift mark for an Extension 2 paper. Just draw the hyperbola xy equals 4. Don't blow the mark, draw it neatly. Yeah. They also want us to show where our hyperbola intersects the axis of symmetry, which would be y equals x. And so those points, well, in case you can't work it out, we're going, xy equals 4, y equals x, so that's x squared equals 4. We get the point 2, 2, and minus 2, minus 2. The second part was to just go and find, go and find the equation of the tangent. In this case, it's xy equals c squared, so c for this one is 2. So the parametrics become 2t, 2 1t. Differentiate, minus 4 on x squared. Sub in, our slope's minus 1 on t squared. Point slope formula. Let's expand and get rid of the fractions, and we get our x plus t squared y is 4t. Now, this is an interesting one. They're telling us s can't equal 0, but also s squared can't equal t squared. We're going to show the tangents at P and another point, which they've given the parameter s, intersect at 4st on s plus t. So The reason s can't equal 0, of course, is because we can't end up with 0 on the bottom of the fraction there. Why can't s squared equal t squared? If s squared was equal to t squared, you could have s equals t, they'd be the same point, and you could have s equals negative t. In that case, the tangents would be parallel. They would never meet. Okay, so we found the tangent at P. I don't have to rederive. I can just use the parameter. So changing the t to an s, we get the tangent is x plus s squared y. Point of intersection, and the y comes out nicely there, we'll see. Right, remember, difference of two squares, dividing by, and we get 4 on s plus t. And subbing back in to work out the x value, we get our 4st on s plus t. So, okay, we have shown they intersect there. The other way I suppose you could do it is to get the answer and substitute it into both equations and show that, hey, look, it works. It does come out to be the same value. I suppose that s is in fact minus 1 on t. We're going to find the locus of m, and we're going to show it's a straight line through the origin, but not including the origin. Okay, we know x is 4st on s plus t, y turned out to be 4 on s plus t, but now we have the condition that s equals minus 1 on t, or another way of thinking about that is s times t is negative 1. We'll have a look at x. If s is minus 1 on t, I get x is minus 4 on s plus t. The relationship between the x and the y now is a very obvious one. So yeah, it's the line y equals minus x, which would be a line going through the origin. It says, but not including the origin. Well, if the point of intersection is 4st on s plus t, and the y value is 4 on s plus t, we're never going to get the origin. Because how can that y value ever be 0? You've got a constant on the top of the fraction. So yes, it's y equals minus x, but as I say, 4 on s plus t could never equal 0, so I'm never going to get the situation where the point of intersection is 0, 0. So it does not include, or it excludes, the origin. Locus questions when it comes to conics. The syllabus is very specific about this. It'll only be on rectangular hyperbola questions. Okay. Now that's not to say you won't get other interesting geometrical properties ones with the ellipse and the hyperbola. But when it comes down to find the locus of, it'll be restricted to the rectangular hyperbola. This is not a hyperbola, in case you were wondering. But I just throw it in now. There is another definition for the ellipse, and that is the sum of their focal lengths is equal to a constant amount. Turns out to be 2a. That's why, I don't know if you've ever done this, if you get your string, 2 pins, and draw, you end up with an ellipse. Because what you're basically doing, that string is like the sum of the 2 focal lengths. It's always the same length, and so you get an ellipse. And there's a very neat little proof. Remember, it's always easier to find vertical or horizontal distances than it is to find ones at an angle. So, definition of an ellipse. I know that PS plus PS dash is equal to eccentricity times PM plus eccentricity times PM dash. Now, if I factorize E, I get PM plus PM dash, which turns out to just be a horizontal line. So I don't have to worry about going to the distance formula, the PS and PS dash, to work it out. I can use that. Well, PM plus PM dash, so the distance between the two directrices must be 2a over E. E's cancel, and it just drops out very nicely. It's just equal to 2a. There's a very similar one with the hyperbola, but it's the difference of the focal lengths rather than the sum of the focal lengths. There we go. 6D and comma. Oh, it's back to M, so it must be an M. Unit 3.